Hello, in the last video we talked about measures of centrality. So roughly, given a set of data, roughly where was the data? In this video we're going to talk about measures of spread, which is given a set of data, how far away are they from the center? So really we're asking, are all the values of this data set really close to each other, really similar to each other? Or are they really different, very far away from each other? How spread out are they? Now, for all the measures of centrality we're going to look at in here, we're going to be talking about interval and ratio data. And why is that? Well, if you think about what we're talking about spread, we're talking about how far away things are from each other. We need that meaningful measure of distance. Talking about spread in things which don't have a distance doesn't make sense. The first measure of spread we look at is called the range. The range is the maximum observation minus the minimum observation, and it gives an estimate of the size of the set of all possible values. It's obviously not the size of the set of all possible values, because when you were doing your recordings you might not have had the maximum or might not have had the minimum, but it gives an estimate of what that size might be. Here's a lot of salaries at some workplace, so 17k, 22k, 43k and so on. What is the range of the salaries here? So we want to find what is the minimum salary and what is the maximum salary. So here the minimum salary is 16k and the maximum salary is 76k. Now you might be tempted to write down the range as this then. The range is between 16k and 76k, and you will see that written down in a lot of casual writing. But that is not the range. The range is the maximum minus the minimum. So the range of this data set is 60k. A very useful measure of centrality is quartiles, which is very related to the median we looked at before. So a quartile, as the name suggests, we split the data into 4 equal parts, and we want to look at where the boundaries are. So the first quartile is a value where 25% of the data lies below it. The second quartile is a value where 50% of the data lies below it. And the third quartile is a value where 75% of the data lies below it. If we were to ask where 0% of the data lie below it, that would be the minimum. Where does 100% of the data lie below it, that would be the maximum. And we tend to use Q1, Q2 and Q3 to denote these. Note Q2 here. Q2, a value where 50% of data lie below it. That is the median. So one of the quartiles is the median. So when we talk about measures of spread, we tend to focus on Q1 and Q3, where does 25% of the data lie below it and 75% of the data lie below it. Using those two quartiles, we can work out the interquartile range. And the interquartile range is the third quartile minus the first quartile. How do we interpret this? Well, it's an estimate of the size of the central 50% of the values. So if the range is the size of 100% of the values, the interquartile range is the size of the set that contains the middlemost 50% of the values. So forgetting all the extreme values, where do 50% of the data lie? Let's have a look at an example. Here is the French national World Cup winning football squad, and here is their ages at the time they won the World Cup. Let's calculate the first quartile, third quartile and the interquartile range for these ages. So just like we did when calculating the median, because they're very related, the first thing we've got to do is put these values in order. Once we've put the values in order, exactly like we did with the median, we need to be able to split this equally into 4 parts. So the second quartile, you found out how to work that before, that is the median. Okay, and the first quartile and third quartile, so you can think of that as what's the middle value of the first half of the data and what the middle value of the second half of the data. So you can just take the first half of the data and find the median of it, and take the second half of the data and find the median of it. So the first quartile here is age 22, the median is age 25, and the third quartile is age 31. The interquartile range then, so the middle 50% of players in this squad lie within 9 years of each other, and the range, so all the squad, lie within 12 years of each other. Now I used really nice numbers here. The reason I chose a football team, not because I'm a football fan, I really don't know what I'm talking about, but because there is a nice number of players here that I can split this equally into 4 nice sections. Once I've taken the median out, I've got an odd number left for the first half and the second half, which I can find the median of. If we didn't have that, how would we work these out? Well, if there are, in general, n values, then the first quartile is quarter times n plus 1. Quarter times n plus 1th term of the series, once you've put them in order. The second quartile is a half times the n plus 1th term of the series, and the third quartile is 3/4 times the n plus 1th term of the series. So there was 11 people in a football squad, a quarter of 12, that would be the third term. So if we look back, the third term was 22 there. That's how I worked out the first quartile. The 12 people in the squad, half 12 is 6, so the 6th term is the median. 3/4 of 12 is 9, so the 9th term would be the third quartile. But what if these don't come out as whole numbers, nice whole numbers? What would we do then? Well, say there are 14 values. This is not going to come out as nice whole numbers. If there are 14 values, what are we going to do? So the first quartile would be a quarter times n plus 1, so a quarter times 15. So it would be the 15 over 4th term. That is the 3.75th term. Does that make sense? Well, remember when we were working at the median and we had 2 middle values and we wanted to find the halfway value? Well, we're going to do the same here, but instead of looking for the halfway value, we're going to look for the 3/4 way value between them, because it's 3.75 between the third and fourth term, 0.75 of the way through. And how do we work that out? Well, we need 3/4 of the fourth term plus a quarter of the third term. So to work out the 3/4 way through, it's 3/4 of the bigger term plus a quarter of the smaller term. So in this case, we allot the 3.75th term. If the third term is 7, the fourth term is 11, is 10. And that's how we would work out the quartiles when there are not a nicely divisible number of values in our data set. A very, very common measure of spread, which you will see a lot, is the variance. And variance is very common because it has some really important downstream uses. The variance is this formula, and essentially what this formula is giving us is the average squared distance from the mean. So remember what the mean was? The mean was the value which minimizes the distance between every term and that value. Now if we take all those distances between every term and that value, the mean, square them so we don't have to care about the sign, whether it's a negative or a positive value, square them, sum them all up and divide by how many are there. So take the average distance away from the mean, we get the variance. But it's the average squared distance. It's squared because we don't care about the sign, whether it's positive or negative. Being far away and above the mean and being far away and below the mean are actually the same distance away from each other. They're just in different directions and we don't care about the direction. So the variance is very interpretable because it has this formula which is the average squared distance from the mean. We use two symbols for variance. So sometimes we use this VAR brackets and the variable x. And sometimes we use this Greek letter sigma with a squared, sigma squared. And that squared reminds us that we are taking the average squared distance away from the mean. Another important and related measure of spread is the standard deviation. And the standard deviation is just the square root of the variance. So you're thinking, why standard deviation? If variance does the job, why do we need to just take the square root of it? It's not telling us anything new. Well, taking the square root of it lets us measure spread with the same units as the mean. So if our mean is in meters, so the average height, for example, the measure of spread, the standard deviation, can also be measured in meters rather than the variance, which would be in meters squared. And it just puts things on the same scale as the mean. Let's look at an example. So calculate the mean, variance and standard deviation of the following 6 rolls of a die. So we've rolled a die 6 times and we get 4, 2, 3, 2, 5 and 1. What's the mean? So we've seen that before. We add them all up and divide by how many are there. So we add them all up, 4 plus 2 plus 3 plus 2 plus 5 plus 1. Divide by how many are there. There are 6 of them there. 17 over 6. What is the variance? So the variance is the average squared distance away from the mean. So for each of our rolls of a die, we take the difference between that roll and the mean. So 4 minus 17 over 6, 2 minus 17 over 6, 3 minus 17 over 6, and so on. Take each of those distances and square them. Remember, when we square a number, we always get a positive number out, so we're actually getting rid of the negatives, just turning them into positives. And then we want to take the mean of that, so add them all up and divide by how many are there. And what is the standard deviation? So the standard deviation is just square root of the variance. So we square root 65 over 36, and that gives us 1 over 6 times root 65 in its simplest form. Why are these 3 things important? These 3 are super useful in downstream tasks. Like I said, the mean is very interpretable. We know how to interpret the variance, and then the standard deviation is we know what the variance is, but now it's on the same scale as the mean. If we want to compare measures of spread across variables which are on different scales, then a useful thing is the coefficient of variation, sometimes denoted with CV. And it lets us compare relative variation. So it takes the variation for one set and the variation of another and scales them down to the same sort of scale so that they're comparable. How does it scale them down? Well, all we are doing is taking the standard deviation and dividing by the mean. Think about something like 2 call centres. One call centre might deal with very trivial complaints, and their phone calls sort of last between 1 minute and 5 minutes on average. Okay? While another call centre might be doing really long questionnaires with people, and they might be on the phone for between 20 minutes and 40 minutes. How can we compare the variation of something on such a small scale to something on such a big scale? Well, the variation of something that's between 1 and 5 minutes, the standard deviation might be about 2 or 3 minutes. 2 or 3 minutes, when on average you're on the phone for about 2 or 3 minutes, is a long time. Sometimes you can be on the phone for double the amount of time or triple the amount of time to your average, and sometimes you can be on the phone for half the amount of time. Whereas on a larger scale, a standard deviation of 2 or 3 minutes, when on average you're on the phone for about 30 minutes, it's hardly anything really. You wouldn't think about it. So even though the measure of variation is the same, your perception of that variation is different. And so if you scale that down by how long you're on average on the phone for, you'll get something that's more comparable. And that's what the coefficient of variation does. And it's a very useful tool for comparing spread across variables which are on different scales.